Okay, this video is for calculus, and this is now that we've defined how parametric equations work and their graphs, their plane curve graphs, now we can do calculus with these parametric equations. This topic is typically split over 2 days, so this is the video for the first day. All right, so the derivative of a parametric function still means slope, like it does for the derivative of a regular function, where y is a function of x, but the way we compute it is slightly different, and it relies on the chain rule. So we know that the slope of a tangent line, so if we're always graphing these curves on the xy plane, right? The parameter is a third variable that shows how y and x on the curve move. The plane itself is still y and x, which means if you have a function curve, a plane curve, even if it's some weird curve that loops around on itself or something, right? The slope of a tangent line at any point is still a change in y and a change in x. It's a little change in y and a change in x. So we still compute the slope of a tangent line as dy dx. Sorry, there's a typo right there, right? dy dx. Okay. But the problem is that we don't have y in terms of x. We have y in terms of t and x in terms of t. So that means if we have x is some function of t and y is some function of t, that means we can take the derivative of this equation, but that would be dx dt. And we can take the derivative of the y equation, but that'll be dy dt. So how do we combine those together? Well, dy dx is simply dy dt. Okay, it looks like I've got something wrong here. Let me fix that real quick. Yeah. Yeah, you can say this. Okay, no, this is fine the way it's written. Dy dt would be equal to dx dt, or dy dx times dx dt, because these dx's would cancel out and leave dy dt on both sides. If you solve that for dy dx is just dy dt divided by dx dt, right? So this is the key point right here, that the derivative dy dx on the xy plane, the slope of the tangent line, is the derivative of the y equation with respect to its parameter t, divided separately by the derivative of the x equation with respect to its parameter t. As long as the bottom derivative isn't zero, then it would be undefined, right? So this is the expression that allows us to get that. And it's easy to remember, right? If you just structure it this way, the dt's would cancel out, leaving you with dy dx. So it makes sense that it would work that way. And you can repeat this for higher order derivatives. If you compute this, though, you'll get a derivative in terms of t. So if you want to take the derivative again and get the second derivative, which is the concavity, right? This derivative over here is the slope. Then you would have to take the derivative of what you just got, and that would be with respect to t. But then to be able to get it with respect to x, you would have to take that and multiply by a dt dx, so that the dt's cancel, leaving an x. So in practice, what we do is we divide again by this dx dt, because dividing by dx dt is like multiplying by dt dx. Right, this is easy to see with a specific example. So let's look you can memorize these as formulas for computing these, but let's just actually go ahead and do an example and see the whole thing. Here is a set of parametric equations. We want to graph the plane curve, but we want to start by finding the dx dt derivative, the dy dt derivative, the dy dx derivative, which is the slope, and the second derivative of y with respect to x, which is the concavity, and then finding those values at two different parameter values, -4 and 1. Okay, so before we graph the plane curve, let's just compute the derivative. Okay, so first, what is dx dt? Dx dt is, we take this equation and take the derivative, so that would be 2t plus 5. Okay, what is dy dt? dy dt is the y equation's derivative, and that would be 4. Okay, so now if we want to find dy dx, that means we have to take dy dt and divide by dx dt, right? And the reason we do that is because the t's will end up canceling out, the dt's will cancel out and leave dy dx, right? So the dy dt is this 2t plus 5, and the dy dx is this 4. So this is an expression for giving me dy dx. Okay, and then if I wanted to write that another way, this is 2/4 t plus 5/4, or 1/2 t plus 5/4. Okay, so just simplifying it. Now I want to do one last derivative, which is the concavity derivative. What is the second derivative of y with respect to x squared? Right, so that means the way we're going to find it is we're going to take the derivative of what we just got. Right, so we're going to take that derivative of this dy dx. Right, but because that has a t in it, when we take this derivative, we have to divide by dx dt again to convert that back into being with respect to x. Okay, so what we would do is first take the derivative of the first derivative, and that would be 1/2. Okay, so derivative of this equation here. Then we have to divide by dx dt again, which we said is 2t plus 5. Okay, so this is the expression for the concavity. And then what we could do is we could come up with some values for this and see what all these values were. They told us to do that at 2 different parameter values. So let's do that. Let's see what is, for the parameter, we'll do the parameter, then we'll do dx dt. Actually, I'll use different colors here. So this is the parameter t. Okay, and then we're going to do next dx dt and dy dt. Right, and then we will figure out what dy dx is. And finally, we'll figure out what the second derivative is. Second derivative of y with respect to x, which is the concavity. All right, so the parameter values they gave were -4 and 1. So if I were to plug -4 into dx dt, that would give me, I'm going to do the work down here. 2 times -4 plus 5 is -8 plus 5, so that is -3. Okay, if I do that with the dy equation, it's just 4. Okay, and if I then compute the dy dx, that is just the dy dt number over the dx dt number. So it's going to end up being 4 over -3. Or if I hadn't previously computed the dx dt and the dy dt, I could just plug the t, -4, right into the expression for that, which would be 1/2 times -4 plus 5/4. It should be, let's see, -8 plus 5/4, which would be negative, let's see, 32/4 plus 5/4, which would be -30. You get the idea, hopefully. Let's see, what is this? -27 over 4, which is the same as this fraction. All right, so here we're coming up with an equation to find the slope at any t. But if you've already computed it for dy dt and dx dt, it's simply the ratio of those two. And then if I were to take the derivative again, now I'm going to actually have to use this formula to find this, because this is a constant, so I can't take the derivative of that. That would give me a 0. Right, so what is this value here? It's 1/2 divided by 2 times the t, which is -4 plus 5. That's going to be 1/2 over -8 plus 5. That's going to be 1/2 over -3, or -1/6. Okay, so this is how you would evaluate all these values. Is that the right value here? Yeah, well, I didn't introduce an error there. Okay. Right, we could do the same thing with 1. And when I did this before, I got the following values. At 1, in my notes here, I get 7. Dy dt turns out to be 4. Therefore, dy dx is this divided by this, which turns out to be 4/7. And the second derivative turns out to be, I just computed it in decimal, it's -0.023. Okay. Right, so it says to graph the plane curve now and interpret the meaning. So We could graph this plane curve a number of ways. We could put it in a calculator and graph. We could try to convert this by eliminating a parameter. For example, we could say that t is y over 4 and substitute that in here and get that this is y over 4 squared plus 5 times y over 4 plus 4. But I think the best thing to do is just show you the result from graphing in a calculator. On the next screen, I've got all the summary of this so we can interpret it. But what I wanted to show you here is that you build up dy dx by taking the derivatives of dx with respect to its variable, dy with respect to its variable, and then you just take dy dt divided by dx dt to get the formula for dy dx. And then when you take the derivative of the next derivative, the concavity derivative, you take the derivative of that previous one, but you have to divide by dx dt a second time so that it changes it back into a function for x's. All right, let's actually look at the interpretation. So here is the graph of the plane curve. It looks like this. There's a plane curve traveling in this direction, right? And let's look at all those values. So what does that mean? The interpretation of dx dt. So what that means is how fast is the point increasing in the x direction per unit of time for t. So for example, at -4, we got a value of -3. And that means that, let's see, well, let's actually plug these values in. If we plug -4 into the actual equations, we get that the xy coordinate is 0, -16. So we're at 0, -16 here at t equals -4. And this derivative, dx dt being -3, means at that location, this is currently moving in this red direction here. It's moving like that, okay? And you can interpret that as moving -3 in the x direction per unit of time. So if this time is like seconds, that means that this trajectory is moving at -3, say, centimeters per second in the x direction, or 3 centimeters per second in the negative x direction. The fact that dy dt here is 4 means that we're moving at 4 centimeters per second in the upward direction also. So we're moving 3 to the left and 4 to the right, right? And then the dx dt, so I'm sorry, the dy dx, this is the slope of the tangent line, which means that you would go, let's see, you would go down 4 for every 3 that you go over. So that gives you the slope of the tangent line, okay? And then the concavity number, the second derivative, which in this case turned out to be positive 0.296 in terms of decimal, that's the concavity. And that means that since that's positive, this curve is concave up in this region. So it is concave in an upward direction here, curving more upward like a cup. Right, so each of these derivatives has a meaning. The dy dx means the slope. The second derivative means the concavity, just like it always does on the xy plane. But these new derivatives, dx dt and dy dt, are how fast the object's moving in the x direction and the y direction per unit of time. Right, and these are unique for every individual place on the trajectory. So if you go over here to t equals 1 and plug that into the function curve, the set of parametric equations, you get that we're at 10, 2, so we're right at this location. Right, the fact that we have a dx dt of 7 means this is moving 7 units per unit of time in the x, so maybe 7 centimeters per second this way, right, and 4 centimeters per second this way, right? And then when you combine those together, it's 4/7. So 4/7 is the slope of this tangent line on the xy plane. And the second derivative means the concavity. So since it's negative, the curve is generally curving down in this region. So each of the 4 derivatives gives a specific meaning. That's the main point of this slide. Okay. Now, if we have the ability to plug in the parameter and get an x and y location, and an ability to come up with an equation for the slope and plug that in and get a slope, once we have an x and a y and a slope, we can build a tangent line, right? This would just be y minus -16, so y plus 16, equals the slope of -4/3 x minus 0. that would be the tangent line here at this location. And if you use the x and y and slope values to build the equation for the tangent line at another place, you get a different line. This is the line that's tangent at that location, at that particular. So every particular parameter value along this path has its own unique tangent line. All right, now when you work with these, you need to be careful because sometimes these curves, since they're not function curves, they don't obey function curve rules, which means they can cross over themselves. So this says graph the curve and find the parameter values where the graph crosses the y-axis. Then write the equations of the tangent lines to the curve at these points. Okay, let's see if we can analyze this before we graph it, just to see what's going on and be aware that there might be more than one thing going on, or more than one point where we're crossing the y-axis. Okay, so to start, we want to know what's going on where, well, first we want tangent lines, right? So for a tangent line, we're going to need x, and we have an equation for that. We're going to need y, and we're going to also have to have the slope. So the slope equation is dy dx, and that means that's going to be dy dt divided by dx dt. So I'm going to have to figure out the equation for the derivative of y with respect to its variable. So taking the derivative of this equation, that's 0. Then we have minus y. Cosine, the derivative of cosine is negative sine, so that will cancel this negative and we get positive sine of t. Positive pi sine of t, that's the derivative dy dt. The derivative dx dt is this derivative, so that's going to be 2. And the derivative of sine is cosine, so 2 minus pi times cosine of t. So now I have an equation that will give me the slope of the tangent line at any parameter value t, and we're just interested from -3 to 3 for the range of t there. All right, so what's interesting here, or what they're asking us to do, is to find the parameter values when the graph crosses the y-axis, right? So crossing the y-axis, well, the y-axis is this axis here, and what's unique about that y-axis is those are places where x is 0. So I can figure out where that happens by taking the x equation. If x has to be 0 and x is 2t minus pi sine t, I can force that to be 0 and try to solve this equation. Right? So that would be, let's see, where will that happen? I don't see an obvious way to solve this, right? There's no way to factor a t out of here because this t is inside of a sine function. So if I could factor, I might be able to find the t values where that happens. I'm going to be forced to use technology to analyze this further. So let's go back to, in the equation here, I'm going to put this calculator into regular functional mode and just graph this equation for x. Right, so I'm going to just enter the equation for that x, which is 2 times the variable minus pi times the sine of the variable. And I'm going to graph that from -3 to 3 for t, because my x variable here represents a t. So I'm going to set my window up to be x. It's from -3 to 3. And then I'm just going to graph this, see what we get. Okay. Okay, so this is the x value, and that means that as this object is moving around, wherever this x is 0, those are places where it's crossing the y-axis. So I'm going to use my technology to find out where those zeros are. Let's see, there's a 0 at, let's see, this one in the middle seems to be 0, so let's find this one over here. This one is, let's see, somewhere between there, and it appears to be here. So that is at -1.57, right? So -1.57, there is a t equals -1.57, which I believe is -pi/2. Let's check that really quickly. Okay, if I just go here and find the other one, I think by symmetry that's the same, but let's verify that. If I find another 0, and I go second trace on there, yeah, there's another 0. Let's find the other one. It appears to be 0 as well, but also this one on the right. I just want to verify that that's the same value, but positive. I think it's -pi/2, 0, and pi/2. Yeah, sure, that's the same. And pi divided by 2 is that number, 1.57. Okay, so it looks like the values are t is negative pi over 2, 0, and pi over 2. Those are the places where the object crosses the y-axis. Okay, so we want to write the equation of the tangent lines there. So what I can do is I'm going to have to find the location of the points. So first I need to know the x and y. Well, we know x is 0 because we found times where that's true. What is the y? Okay, when y, so if y is 2 minus pi cosine t, I can try plugging in negative pi over 2 into that. 2 pi cosine of negative pi over 2. On a unit circle, negative pi over 2 is here. The cosine is negative 1. That's negative 1 times pi. So this can be 2 minus negative, so 2 plus pi. So this would be 2 plus pi, right? There's the location of that, which in decimal would be, see, 2 plus pi. It doesn't seem right. Is that right? Yeah, let me actually just use, you know what, since we're using technology anyway, let's go ahead and enter the equation for y. So y would be 2 minus pi times the cosine of the variable. And so now if I go to the table here, I could enter negative pi over 2, negative pi divided by 2, no, as the t value, and this y1 is actually the x coordinate and the y2 is the y. So that is 0, 2, okay? So let's record this. Thinking rather than doing it by hand, we'll just record this as a result. So parameter value, t, negative pi over 2 is one of the interesting locations, 0 and pi over 2. First, we need the x, y location. And so we just found out that if we plug negative pi over 2 in there, we get 0, 2 as the xy coordinate. I could also plug in 0 here, and that would give me 0, negative 1.142, negative 1.142, and then if I plugged in positive pi over 2, that's going to give me 0, 2 again. Okay, so this means that both of these two times, the object is at that same location, 0, 2. I haven't graphed it yet. I'm just doing this all analytically. Now, let's also figure out what the slope is at these values. Slope is dy dx. So I'm going to add one more equation into the calculator since we're just using technology for this. The third column is going to be the slope, which is, let's see, pi times sine of the variable t divided by parentheses 2 minus pi times the cosine of the variable t. Close the t, cosine goes to the bottom. Okay, now if I go back to the table, and I go to these locations, there should now be another column here that gives me the slope. So the slope here is negative 1.571, and the slope at this location is 0. And the slope at this one is positive 1.571. Okay, so what would be the tangent equation? Tangent equations here would be, let's see, y minus 2 equals negative 1.571 for the slope times x minus 0. For this location at t equals 0, we would have y minus negative, so y plus 1.142 equals 0 for the slope times x minus 0, which would therefore just be the line y equals negative 1.142. And then this tangent line would be y minus 2 equals the slope of positive 1.57 times x minus 0. So 3 unique tangent lines at these points. So even though you're at the same location, you might have a different tangent line with a different slope. Okay, now I'm going to display what the graph is. And if we were to do this in polar, actually we could just do that now that we've got this. We could go to parametric mode, and graph the equations by entering 2t minus pi times sine of t for the x, and for y it is 2 minus pi times cosine of the parameter. And that's not there, the square. Let's get rid of that. Okay, so if I graph that, now this is by default going from 0 to 2 pi. Let me change this to go from -3 to 3. And we'll see what that looks like. All right, so this is what the shape looks like. And now that we've seen that in the calculator, here's a close-up graph of that. It looks like this. And I want to point out a few things about it. It does cross, the path is moving like this. It crosses the axis 3 times. The first time at t equals -pi/2. Then it crosses down here when t equals 0, and then it crosses again at t equals pi/2. And for each one of those, there's a unique tangent line, right? The first time it crosses, the tangent line has a negative slope of -1.57. At the middle point, it has a horizontal slope. The slope was 0, so a horizontal tangent line. And then as we went the rest of the way, it had a positive slope. Right? So you have to be careful when you have complicated graphs like this. You might have a place that is the same location in space, but it's not there at the same time, and therefore each time it gets there, it has a different tangent line and a different trajectory. Okay. So another thing, and a very common thing that can happen on AP exams, is they'll ask questions about at what parameter value or what are the xy locations where we have horizontal tangents or vertical tangents. So what makes a tangent horizontal? A horizontal tangent occurs when the slope of the tangent line is 0, like this one down here. Right? So you're looking for a place where the slope is 0. And since the slope is dy dx, and we know the dy dx is dy dt over dx dt, right? For this function to be 0, the numerator has to be 0. So that means that horizontal tangents occur when the dy dt equation's derivative is 0, when the y equation's derivative is 0. Okay, vertical tangents occur when you're about to divide by 0 and get an infinite slope, right? Like the slope would be some, say, positive number here, but this positive number is getting, it's going from 10 to 100 to 1,000 to 1,000,000, and right at this vertical tangent, the slope is effectively infinity because you're about to divide by 0. So we will have a vertical tangent when the denominator is about to go to 0. When that goes to 0, when dx dt goes to 0, that's where you get vertical tangents. Okay. All right, so you're looking for when the whole slope would be undefined, which is when the denominator is 0. So the thing to remember is that horizontal tangents happen when the numerator is 0, and vertical tangents happen when the denominator is 0. Okay, then there is one more example here. I think hopefully, yeah, this is the last one because this video is already pretty long. Let's say that we have a baseball hit by a bat. Its trajectory is given by this. What is the angle of elevation of the path at 3 different times? So what would that mean? Well, if you imagine you had let's say we have an XY plane, and at time 0, let's see, just really quickly, if we plug a 0 in here, x is 0, this is 0, so you're going to get some y, so it's starting out at some y, and then it gets hit, and x is just kind of continuing straight, but this is going through some sort of downward parabola. So the path is like this somehow, right? At any particular point, what is the angle of elevation? Well, if you figure out the slope of the tangent line, right, the angle of elevation would be this angle here. And if I know what the y is over the x, so the dy over the dx, that tangent of that angle of elevation would just be the dy over dx. And that means that you can find the angle of elevation by taking the inverse tangent of the slope, dy dx. Okay, so what we could do is calculate the slope. So we know that the slope is dy dx, and that is therefore dy dt over dx dt. Right, so what is the dy dt? Well, the derivative of that is 0. The derivative of this is you bring the 2 down here, so it's minus 2 times 77 over 2500, t minus 50 to the first power, and then times the derivative of inside is 1. So that's the top of the equation. And then the bottom of the equation is the derivative dx dt, which is simply 1. Right, so this is the slope, and therefore the angle of the elevation is the inverse tangent of that slope, negative 2 times 77 over 2500, and then this would be t minus 50. Right, so you can plug any t in here and then compute the inverse tangent to find that. Okay, we've already gone pretty long on this video, so I'm just going to show you the result. You would end up getting that the slope is, if you wanted to go into degrees, it would be 72 degrees as the baseball left the bat, but at 30 seconds in, it's not as steep, so only 50 degrees. And at 80 degrees, you're past the peak height, and so the slope is actually negative. We'd have a negative angle of elevation of 31.633 degrees. All right, what do the derivatives mean? Again, they mean how fast the ball is moving in the upward direction. That's dy dt. Dx dt is how fast it's moving downrange. All right, that's enough for that. We have a much shorter video for the second day of the topic, but this should hopefully help you with the first day's homework.